Hi students, what we are going to do here is talk about the standard addition algorithm. So an algorithm is the series of steps that you learn in order to perform a mathematical task. So you learned algorithms to do addition, subtraction, multiplication, division, all with whole numbers. You have learned algorithms to do lots of things in mathematics. So an algorithm is different than an approach. An approach is, how do I think about an operation so that I understand it? Example, the sharing approach for division, apples and buckets. So a student can understand, figure out how to get an answer by approaching the problem with a certain mindset. An algorithm is when we want the students to essentially get fast at being able to perform operations or some other mathematical task. But we don't want them to memorize algorithms just as a series of steps. If they don't understand why the steps of the algorithm are what they are, then they're going to make mistakes, they're going to forget, they're going to not be able to apply it to further learning and all that kind of thing. So you're used to hearing me talk about that a lot, that the understanding is very important. So for each operation, and we're going to start with addition here, we are going to use base blocks to demonstrate why we do what we do in the standard algorithm. So we've got an addition problem here represented. So we've got 43 plus 38. And my guess is if I asked you to get the answer to that, you would, without really doing much thinking, 8 plus 3 is 11, put down the 1, carry the 1, 4 plus 3 plus 1, so on. And you really wouldn't think about it. And I'm not sure, at least in my experience, most students are not able to explain what they mean when they say carry the 1 and so on. So let's take a look at this. And what we're going to do is look at it from a child's perspective. So we are representing the 43 up here. So we've got 4 longs. And we've got the 3 ones. And I want to come over here on the sketch to show you also that, we have to be able to represent this on paper sometimes without the actual pieces. So we could also do just long, oh boy, this is going to be bad, huh? Long, baby, baby, baby. Okay? And then to represent the 38, 3 longs, 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is much prettier, obviously, but we can still do the problem. All right, so when a child approaches this, they might try to do the 10s first to combine them together. A lot of them will naturally do the 1s first. The standard algorithm does the 1s first. Doesn't mean you have to, but that's what the standard algorithm does. So we take a look at how many 1s we have. There's 3 up here, and there's 8 down here, so that's a total of 11. Now, if students have been working with base blocks all along, it is of no consequence to them to look at that and say, well, I can't have 11 1s or babies or whatever it is they call them. I need to trade that in. So I'm going to move this out of the way a little bit. And then this very cool program allows me to lasso these, and I have intentionally put 10 babies inside that lasso, and ta-da! So this is giving me the hint, hey, this is the column for 1s. This doesn't belong here, so I need to move it over to the other column. Now, I didn't have to move it up here, it just needed to go over here with the 10s. So then I need to look at my 10s. I've got 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 10s. So if I go back to my paint program, and I don't have this cool tool, this NLMV manipulatives, I said that wrong, NLVM, what you can do is show it like this. So essentially, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably shouldn't have had to count those, but I did. And you can show the same thing. There's my lasso. Come over here. Add my 1. So I've got 1, and then I've got 8. And of course, what we're doing with the base pieces mimics what they're going to start doing symbolically with the algorithm. So we want students to work with the base pieces for a while alone, then do both, and then eventually just be really good at doing the symbolic manipulation. So let's do one more problem here. So let me clear this screen. And I'm going to see what problem it randomly generates for me. Ah, nice big one. Okay. So we'll do it over here first, and then again I'll quickly show you how it's represented if we're just doing a drawing to make sure you're okay with that. So I start with my 1s, and I must like this 3 and 8 thing because I've got the exact same thing here. So I need to take 10 of those, and I'm going to move that over, and this time just to prove my point, I didn't have to put it on top. I can just get it over into my tens column, and there we are. All right, I've got a lot of longs here, a lot of 10s, too many. So I'm only allowed to have 9. If I have 10, I need to make flats out of them. So let me lasso 10 of these. Right, and I will move this over. Now I have a feeling this is going to be kind of hard to see what's going on. Alright, so it looks like I've got 4 up top, and then I need 5, 6, 7, 8, 9, 10. So I'm trying to sort out, so when I try to lasso these, I get 10 of them. We'll find out if I was successful. Hopefully I am. Or not. Let's try it again. Let's see if we're having those. There we go. All right. So I had 10 flats. Those make a block, and it gets moved over. So we can see I've got 1 1,000. 1 100, matching right over here, right? I've got 6 10s, and I have 1 1, or 1 baby. So we can also see the 2 regroupings that happened, and represented with these 1s up here showing I had to take the new piece I formed and moved it to the other column. Okay, so just very quickly, if I wanted to show this with base pieces, I would, this would be 3 flats, 7 longs, 3 1s, and then I've got 7 flats, 8 longs, and 8 1s. So I can show the same thing. There's my 10 babies that have been lassoed, and then we just show that it gets moved over. And then I need to get 10 longs. And that gets moved over. And I need to take 10 flats. Make 1 left there. And that makes a shadow, a block, whatever we want to call it. So then my answer, I've got 1, 1, 6, 1. Okay, students, so in my mind, this is where things get really fun. In order for you to really have a deep understanding of the algorithms for addition, subtraction, multiplication, division, we need to do more than just have you work on them in base 10. So I want you to experience what it's like for your students to learn those algorithms the first time. And the way to make you have that experience, rather than just trying to erase your brain, which I can't do, is to have you perform these algorithms with numbers in different bases. So I have a base 5 problem written here, And it does not have the 5s on here, but this is in base 5. Notice that there are no digits bigger than 4. And if you look at the base pieces, you can say, all right, babies are babies. My longs are made up of 5 babies. My flats are made up of 5 longs, which is a total of 25. 5 flats would make a block, which would be 125, and so on. So I'm definitely in base 5 here. So, again, the cool thing is with using shortcuts to represent blocks is that if I'm going to draw this, I am not going to worry about anything other than just saying, hey, I've got some flats here. Flats, longs, babies. And it's up to me to know how many for my exchange rate. Okay, so there's my picture. All right, so when I do this problem, let's see, begin problem, I need to do the same thing as last time, but I'm in base 5. So my exchange rate has changed so that I am going to gather 5 babies, and I am going to make a long out of that, and I'm going to move it to my longs. So my longs are 5s now, not 10s, they're 5s. And then I'm going to repeat the process. So 5 5s makes a 25. And I'm going to move that over. And I'm going to repeat the process again. I'm going to try to repeat the process again. There we go. 5 25s is a 125. So it gets moved over. So then you can see I've got one block, which is in the blocks column or the 125s column. I've got one flat, which is a 25s column. I have 0 5s, and I have 1 1. And again, you can also see this carrying process that was going on. As I gathered together 5 of the babies, it made a long, and I had to account for that and put that in my column there. So I can do the same thing over here. It's like last time. So those come over, and I make a long. All right, I pretend like I got all of them. I make a flat. I take 5 flats. And I make a block. So I have 1, 1, 0, 1 as my answer. All right, so here we go with a problem. This time we are in base 3. You can tell that because it's labeled 1s, 3s, 9s, 27s. I wish that they would write on this, but you know, this is a beautiful program anyway for us to be using. The base 3 on there. So when we're using base 3, we've got a different exchange rate. We are in 3s. So when I begin this problem, I'm going to take 3 of my 1s and make a 3 out of that. And I've only got 2 3s, so that's fine. So you can see it's already been recorded down here. I do have 3 9s, and I want to take those and make a 27. So then I have 1 27, 0 9s, 2 3s, and 1 1. And again, you can see the carrying that's going on here. You can see how what we write for the standard algorithm, what we think for the standard algorithm, matches up beautifully to what happens with the base pieces. All right, so let's give a try now to doing a problem without the base pieces. You can use them all you want. So if you cannot do these problems without the base pieces, just use the base pieces. Don't worry about it. But I want to kind of talk through this. We've got, actually, I'm going to have to do that in the next screencast. That's it.